It's great to be here. So one of the most important industries, of course, is telecommunications. Just as the world's cloud data centers have now become software-defined, it stands to reason that telecommunication should also be software-defined. And so that's the reason why we've taken now some 6 years to refine and optimize a fully accelerated radio access network RAN stack that does incredible performance. For data rate per megawatt, or data rate per watt, we are now on par with the state-of-the-art ASICs. And so once we could do that, once we could achieve that level of performance and functionality, then after that we can layer on top AI. And so we have great partners here. You could see SoftBank and T-Mobile, Indosat and Vodafone are doing trials. Nokia, Samsung, Kyocera are working with us on the full stack. Fujitsu and Cisco are working on the systems. And so now we have the ability to introduce the idea of AI on 5G or AI on 6G along with AI on computing. We're doing that with quantum computing. Quantum computing is still at the noisy, intermediate scale quantum, called NISQ. However, there are many, many good applications we could already start to do. And so we're excited about that. We're working on a quantum classical or quantum GPU computing platform. We call it CUDA-Q, working with amazing companies around the world. GPUs could be used for pre-processing and post-processing, for error correction, for control. And so in the future, I predict that all supercomputers will have quantum accelerators, all have quantum QPUs connected to it. And so a supercomputer would be a QPU with QPUs and GPUs and some CPUs. And that would be the representation of a modern computer. In the last several years, we've been working on a new computer to make it possible for us to do inference time scaling, or basically thinking incredibly fast. Because when you think, you're generating a lot of tokens in your head, if you will. You're generating a lot of thoughts, and you iterate in your brain before you produce the answer. So what used to be one-shot AI is now going to be thinking AI, reasoning AI, inference time scaling AI. And that's going to take a lot more computation. And so we created a new system called Grace Blackwell. Grace Blackwell does several things. It has the ability to scale up. Scale up means to turn what is a computer into a giant computer. Scale out is to take a computer and connect many of them together and let the work be done in many different computers. Scaling out is easy. Scaling up is incredibly hard. Building larger computers that is beyond the limits of semiconductor physics is insanely hard. And that's what Grace Blackwell does. Grace Blackwell broke just about everything. And all of you in the audience, many of you are partnering with us to build Grace Blackwell systems. I'm so happy to say that we're in full production, but we can also say it was incredibly challenging. Although the Blackwell systems based on DGX has been in full production since the end of last year and has been available since February, we are now just putting online all the Grace Blackwell systems. They're coming online all over the place every single day. It's available in CoreWeave now for several weeks. It's already being used by many CSPs. And now you're starting to see it coming up from everywhere. Everybody's starting to tweet out that Grace Blackwell is in full production. In Q3 of this year, just as I promised, every single year, we will increase the performance of our platform every single year like rhythm. And this year, in Q3, we'll upgrade to Grace Blackwell GB300. The GB300 will increase the same architecture, same physical footprint, same electrical and mechanicals, but the chips inside have been upgraded. It has upgraded with a new Blackwell chip. It's now 1.5 times more inference performance, has 1.5 times more HBM memory, and it has 2 times more networking. And so the overall system performance is higher. All of that is so that we could build a very large chip. And NVLink and Blackwell, this generation, made it possible for us to create these incredible systems. Here's one from Pegatron and QCT and Wistron and WeWin. This is from Foxconn and Gigabyte and ASUS. And you could see the front and the back of it. And its entire goal is to take these Blackwell chips that are, you could see how big they are, and turn it into one massive chip. Now, the ability to do that, of course, was made possible by NVLink. But it understates the complexity of the system architecture, the rich software ecosystem that connects it all together, the entire ecosystem of 150 companies that came together to build this. This architecture and the entire ecosystem in technology, in software, in industry has been the work of 3 years. This is a massive industrial investment. And now, we would like to make it possible for anybody who wants to build data centers. It could be a whole bunch of NVIDIA GB200s or 300s and accelerated computing systems from NVIDIA. It could be somebody else. And so today, we're announcing something very special. We're announcing NVIDIA NVLink Fusion. NVLink Fusion is so that you can build semi-custom AI infrastructure. Not just semi-custom chips, because those are the good old days. You want to build AI infrastructure. And everybody's AI infrastructure could be a little different. Some of you could have a lot more CPUs, and some of it could have a lot more NVIDIA GPUs, and some of it could be somebody's semi-custom ASICs. And those systems are so insanely hard to build. And they're all missing this one incredible ingredient. This incredible ingredient called NVLink. NVLink so that you could scale up these semi-custom systems and build really powerful computers. And so today we're announcing the NVLink Fusion. NVLink Fusion kind of works like this. This is the NVIDIA platform, 100% NVIDIA. You got NVIDIA CPU, NVIDIA GPU, the NVLink switches, the networking from NVIDIA called Spectrum-X or InfiniBand, NICs, network interconnects, switches, and all of the entire system, the entire infrastructure built end-to-end. Now, of course, you can mix and match it if you like, and we now today make it possible for you to mix and match it even at the compute level. This would be what you would do using your custom ASIC. And we have great partners I'll announce in a second who are working with us to integrate your special TPU or your special ASIC, your special accelerator. And it doesn't have to be just a transformer accelerator. It could be an accelerator of any kind that you would like to integrate into a large scale-up system. We create an NVLink chiplet. It's basically a switch that abuts right up to your chip. There's IP that will be available to integrate into your semi-custom ASIC. And then once you do that, it fits right into the compute boards that I mentioned, and it fits into this ecosystem of an AI supercomputer that I've shown you. Now, maybe what you would like is you would like to use your own CPU. You've been building your own CPU for some time, and maybe your CPU has built a very large ecosystem, and you would like to integrate NVIDIA into your ecosystem. And now we make it possible for you to do that. You could do that by building your custom CPU. We provide you with our NVLink chip-to-chip interface into your ASIC. We connect it with NVLink chiplets, and now it connects and directly abuts into the Blackwell chips and our next generation Rubin chips. And again, it fits right into this ecosystem. DGX Spark will be ready, will be available shortly, probably in a few weeks. We have tremendous partners working with us. Dell, HPI, ASUS, MSI, Gigabyte, Lenovo. Incredible partners working with us. And this is the DGX Spark. This is actually a production unit. This is our version This is our version. However, our partners are building a whole bunch of different versions. This is designed for AI native developers. If you're a developer, you're a student, you're a researcher, and you don't want to keep opening up the cloud and getting it prepared, and then when you're done scrubbing it, okay? But you would just like to have your own, basically your own AI cloud sitting right next to you, and it's always on, always waiting for you. It allows you to do your prototyping, early development, and this is what's amazing. This is DGX Spark. It's 1 petaflops and 128 gigabytes. In 2016, when I delivered DGX1, this is just the bezel. I can't lift the whole computer. It's 300 pounds. This is DGX1. This is 1 petaflops and 128 gigabytes. Of course, this is 128 gigabytes of HBM memory, and this is 128 gigabytes of LPDDR5X. The performance is in fact quite similar. But what's most important is that the work that you could do, you could work on this, is the same work you could do here. It's an incredible achievement over just the course of about 10 years. Okay, so this is DGX Spark for anybody who would like to have their own AI supercomputer. And it's, I'll let all of our partners price it for themselves, but one thing for sure, everybody can have one for Christmas. Here's one. This is another desk side. This is also going to be available from Dell and HPI, ASUS, Gigabyte, MSI, Lenovo. It'll be available from Box, from Lambda, amazing workstation companies. And this is going to be your own personal DGX supercomputer. This computer is the most performance you can possibly get out of a wall socket. You could put this in your kitchen, but just barely. If you put this in your kitchen and then somebody runs the microwave, I think that's the limit. And so this is the limit. This is the limit of what you can get out of a wall outlet. And this is a DGX station. The programming model of this and the giant systems that I showed you are the same. That's the amazing thing. One architecture, and this has the ability, enough capacity and performance to run a 1 trillion parameter AI model. Remember, Llama is Llama 70B. A 1 trillion parameter model is going to run wonderfully on this machine. Okay, so that's the DGX station. This is the brand new RTX Pro Enterprise and Omniverse server. This server can run everything. It has x86, of course. It can run all of the classical hypervisors. It runs Kubernetes in those hypervisors. So the way that your IT department wants to manage your network and how they want to manage your clusters and orchestrate workload works exactly the same way. It has the ability to even stream Citrix and what other virtual desktops to your PC. Everything that runs in the world today should run here. Omniverse runs on here perfectly. But in addition to that, this is the computer for enterprise AI agents. Those AI agents could be only text. Those AI agents could also be computer graphics. Little TJs, coming to you, little toy Jensens coming to see you, helping you do work. And so those AI agents could be either in text form, it could be in graphics form, it could be in video form. All of those workloads work on this system. No matter the modality, every single model that we know of in the world, every application that we know of should run on this. In fact, even Crisis works on here. Okay, so anybody who's a GeForce gamer? There are no GeForce gamer in the room. So in order for robotics to happen, you need AI. But in order to teach the AI, you need AI. And so this is really the great thing about the era of agents where we need a large amount of synthetic data generation, robotics, a large amount of synthetic data generation, and skill learning called fine-tuning, which is a lot of reinforcement learning, and enormous amount of compute. And so this is a whole era where the training of these AI, the development of these AI, as well as the running of the AI needs an enormous amount of compute. Well, as I mentioned earlier, the world has a severe shortage of labor. And the reason why humanoid robotics is so important is because it is the only form of robot that can be deployed almost anywhere brownfield. It doesn't have to be greenfield. It could fit into the world we created. It could do the tasks that we made for ourselves. We engineered the world for ourselves, and now we could create a robot that fit into that world to help us. Now, the amazing thing about human robotics is not just the fact that if it worked, it could be quite versatile. It is likely the only robot that is likely to work. And the reason for that is because technology needs scale. Most of the robotic systems we've had so far are too low volume. And those low volume systems will never achieve the technology scale to get the flywheel going far enough, fast enough, so that we're willing to dedicate enough technology into it to make it better. But humanoid robot, it is likely to be the next multi-trillion-dollar industry. And the technology innovation is incredibly fast. And the consumption of computing and data centers, enormous. But this is one of those applications that needs 3 computers. One computer is an AI for learning. One computer is a simulation engine where the AI can learn how to be a robot in a virtual environment, and then also the deployment of it. Everything that moves will be robotic. As we put these robots into the factories, remember, the factories are also robotic. Today's factories are so incredibly complex. This is Delta's manufacturing line, and they're getting it ready for a robotic future. It is already robotics and software defined, and now in the future there will be robots working in it. In order for us to create robots and design robots that operate as a fleet, as a team, working together in a factory that is also robotic, we have to give it Omniverse to learn how to work together. And that digital twin, you now have a digital twin of the robot, you have a digital twin of all of the equipment, you're going to have digital twin of the factory. Those nested digital twins are going to be part of what Omniverse is able to do. This is Delta's digital twin. This is WeWin's digital twin. Now, while you're looking at this, if you look at it too closely, you think that it's in fact photographs. These are all digital twins. They're all simulations. They just look beautiful. The image just looks beautiful, but they're all digital twins. This is Pegatron's digital twin. This is Foxconn's digital twin. This is Gigabyte's digital twin. This is Quanta's. This is Wistron's. TSMC is building a digital twin of their next fab. As we speak, there are $5 trillion of plants being planned around the world. Over the next 3 years, $5 trillion of new plants. Because the world is reshaping, because reindustrialization moving around the world, new plants are being built everywhere. This is an enormous opportunity for us to make sure that they build it well and cost effectively and on time. And so putting everything into a digital twin is really a great first step and preparing it for a robotic future. In fact, building that $5 trillion doesn't include a new type of factory that we're building. And even our own factories, we put in a digital twin. This is the NVIDIA AI factory in a digital twin. Kaohsiung is a digital twin. They made Kaohsiung a digital twin. There are already hundreds of thousands of buildings, millions of miles of roads. And so, yes, Kaohsiung is a digital twin. Not only are we creating the next generation of IT, we are in fact creating a whole new industry. This whole new industry is going to expose us to giant opportunities ahead.